Being shared. I seems a little silly. It's a FERPA regulation that I have to do that. So we have a few things to talk about today. They're sort of lumped together in the same textbook section, but they don't have much in common that I can see. So U substitution, as we have stated it, is a technique for finding indefinite integrals, antiderivatives, but at least for now, the main application of finding these antiderivatives is using the fundamental theorem of calculus. So we might be faced with a problem like the integral from 1 to 3 of 5 over 2x plus 3 dx. And this doesn't look that much like a U substitution problem at first blush. There's no obvious composition going on here, but we talked about this type of example at the end of day Monday. We talked about how you can try letting U be the denominator of the fraction. And I mean, just as a slight aside, this isn't a cure all works in every situation trick. There are no works in every situation tricks. If instead of a 5, in it. So this works in this situation. We're going to see later in the class, though, that integrals that look like this are pretty common, that they show up a lot when we're dealing with rational functions. And U substitution does work for this integral. And there are sort of two ways that we can do this. There's a way that the textbooks like, and there's a way that the students like, if I can make a kind of generalization. So we can see both of these, and we'll start with what I'll call the student method, although I like it too. This isn't a pejorative use of that word. So the student method is to say, well, to take this, we need an antiderivative. And once we found the antiderivative, we'll stick in 1 and we'll stick in 3 and we'll subtract them. So let's find the antiderivative. And we'll go to a blank part of our page, or in this case, a blank screen on the whiteboard. And we'll find the antiderivative. I guess I should say the definite integral. The indefinite integral. Sorry, it's early for me too. So we'll find the indefinite integral using U substitution. Again, this is indefinite. You'll see that I don't have any numbers here. Probably have asked you to do this, but it's a little late now. If we let u be 2x plus 3, du is 2dx. We have a 5 and we don't have a 2, but both of those problems are fixable. That 5 we can just pull out. And as for the 2, we can multiply it in. At the same time, we'll divide by it. So we're not actually changing anything. And now we have a 1/2 that we don't want. But that's also not a real problem. We can deal with that 1/2 just as we dealt with the 5. 5/2, the integral of 1 over 2x plus 3. And just for emphasis, let me move that 2 over here. And now 2dx is a du. So that's going to turn into du. 2x plus 3 is u. So that's going to turn into 1 over u. And we have that 5/2 out front. 5/2, the natural log of, I think everything's positive here, but just to be meticulously correct, we put the absolute value in. 5/2, the natural log of the absolute value of u, running out of space, but we got there with just inches remaining. And I'm including the plus c here because I'm finding an indefinite integral. We're not going to use the plus c, but it's good to be cautious and correct when you're doing mathematics, even if it sometimes comes across as a little persnickety. So now that we've found the indefinite integral, we can go back to this frame. There's an antiderivative. We no longer write the plus c because we're using the fundamental theorem. 5/2, the natural log of, stick this 3 in, 6 plus 3 is 9, minus 5/2, stick this 1 in, 2 plus 3 is 5. And we could go to our calculator and get the decimal approximation of that, but I think it's fine as an answer. So, I mean, that was, I won't say easy if this is the first time you're seeing this stuff, but it's a pretty straightforward, I would say, application of the fundamental theorem. We need an antiderivative. We find an antiderivative. Once we found the antiderivative, we stick in the limits and subtract. So here's an alternative. And I'm calling this the textbook method. That's not quite true. The textbook goes over both methods, but I think it prefers this one. So not 1, sorry, 5 over 2x plus 3. So the idea here is that we're going to just sort of solve this in one step. Instead of first finding the antiderivative, we're going to, well, you'll see. I mean, to take the antiderivative, we need u to be 2x plus 3. du equals 2dx. And we can perform the same sort of messing around that we performed previously. That 5 can come out of definite integrals, just like indefinite integrals. And we can put in a 1/2, and we can put in a 2. And we can get here. This is identical to what we were doing in the first few steps back here. I wrote this slightly differently, but obviously if I'd wanted that 2 in the numerator, it could have gone there. And now I say, or rather, I don't say this is an error. Okay, so we've got 5. We're going from 1 to 3. We can do the u substitution now. We're going from 1 to 3. The antiderivative of 1 over u is the natural log. So we get 5/2, the natural log of 3 minus the natural log of 1. And I've written this down, but I've obviously also written down that this is a mistake, that we've made an error here. And the error comes from the limits of integration. So when we have a function like 2 over 2x plus 3, I don't know what it looks like. Let's just say it looks like this. And we're integrating from 1 to 3. Well, here's the x-axis. And here's x equals 1. And here's x equals 3. All right. So I perform a u substitution, and my variable is no longer x. My variable is u. So now I've got a u axis instead of an x-axis. But my limits of integration don't make sense anymore. If I've got a u-axis, I cannot be going from x equals 1 to x equals 3. So the limits of integration cannot be 1 and 3. What I can do is I can say, well, u is 2x plus 3. So x equals 1. Well, when x is 1, what's u? 5. 2 times 1 plus 5. And when x equals 3, what's u? 9. So I can say, well, now my variable is u instead of x. And instead of going from x equals 1 to x equals 3, I must be going from u equals 5 to u equals 9. And now I use the fundamental theorem as sort of as usual. We stick in the 9, we stick in the 5, and we wind up with the same thing that we got previously. 5 halves ln 9 minus 5 halves ln 5. And I mean, it's easy to see why a textbook might like this, because from the textbook's point of view, this is extremely clean. Like, here we covered 2, frames of the whiteboard. We had to go somewhere else and we had to find the indefinite integral. And then once we found the indefinite integral, we went back here and we plugged it in. Here we used 1 frame or half a frame. We found the indefinite integral and we used the fundamental theorem of calculus. And we did have to make this little adjustment. I don't care how you solve problems like this. The only problem I see is when students make, this is no longer an error, this is now correct. But do not adjust the limits of integration. Any questions about this? So the next piece of material, it's the same textbook section. Very related. It's talking about area. Area between curves. So the integral and area are related to each other. I mean, back in Math 151, this is how we introduce the definite integral. We give an example, we say that, the area under a velocity curve is distance. So how do we find this area? And we say, well, if here's our curve, we talk about area under the curve, which is always a slightly fuzzy statement because the area under the curve is infinite. But what we really mean is this area, the area between the curve and the x-axis. We say, well, if this is A and this is B, then this area is the definite integral of f of x. And this is true as long as f of x is positive. If f of x is ever negative, it becomes a weighted area. We can talk a little about that tomorrow or Thursday. So now, instead of under, we see the word between. So now, instead of having one curve, we have two curves, and we've still got limits of integration. We're still going from A to B. And we want the area between these curves. And we'll talk about why in a moment. This is much more important than it probably looks. But for now, let's try to find a formula. And I'm not going to derive the formula in great depth, but fundamentally, we find the formula using the same Riemann sum strategy we used back in Calculus 1 when we were learning to do this. We can build rectangles. Going to get sick of this very quickly and say that you get the point. We can cover that region with rectangles, and we can find the area of rectangles. And when we've done all of that, we'll have an approximation of this area. And if we build our rectangles, by taking a point, x sub 0, and using that x sub 0 to find the min and find the max. And we define the width of the rectangle to be delta x. This is f, this is g. Then the area of that rectangle is f of x sub 0 minus g of x sub 0 delta x. This f of x sub 0 minus g of x sub 0 is this distance. This is f of x sub 0, this is g of x sub 0. To find the distance, we subtract the smaller number from the bigger number. We do that a bunch of times, and we add our approximations up, and we get our Riemann sum. Our Riemann sum becomes better the more rectangles we use. We let the number of rectangles we use go to infinity. And this is now an integral. This is the definition of the integral is the limit of Riemann sums. This is now the integral from A to B of f of x minus g of x dx. And we can do, and we will do, examples, and we'll look at, complications that can arise. Before we do any examples, I'd like to talk a little about what this is for, because the textbook really does not explain that. The textbook makes this look, I mean, this has a bunch of sort of geometric stuff, and it really fails to explain why areas specifically are so important. But the area between curves is especially important. It shows up in many applications. This is sort of the real part of this statement. It shows up in many applications where there is no mention of area. I mean, it's easy to make up kind of fake applications. You have a oddly shaped room and these curves give the width of the room, and you want to paint the room. How much paint do you need? Oh, that's obviously a kind of fake application. Let's see how this is used. Or let's give one application out of many from the world of business and economics. And I'm not going to say anything about oddly shaped rooms. I'm going to which is not an application that you might, off the top of your head, imagine that the area between curves is going to show up. Yeah, I have. So the Lorentz curve, or the Lorentz function, is a function in economics. And this is one of those real world functions where you can't write down a nice equation for it in terms of the sine and the cosine, but you can look at a country and figure out what the Lorentz curve is. So L of x is the proportion of a country's wealth that the poorest proportion x of the population control. And probably when I just write that on the board, it's a little inscrutable, but I hope an example will quickly clarify it. So in America, you hear a lot about the 1%. That 1% of America's wealthiest people control a significant or disproportionate amount of America's wealth. So This number was from a few years ago, and it might have changed. But for America, L of 0.99 is about 0.67. So the poorest 99% of American citizens control about 67% of America's wealth. And as I say, this is usually talked about in a kind of converse sort of way. If the poorest 99% control 67% of America's wealth, then the richest 1% must control about 33%. Let's try that again. Control about 33% of America's wealth. So the Lorentz function is a measurement of wealth inequality. And we can look at two different countries, and we can ask, how does wealth inequality vary between these countries? Like, assuming that you think wealth equality is a goal that is worth pursuing, is America better or worse off than Canada? A question like that is a question it would make sense to ask. So to answer that question, we'll ask what wealth equality would look like. So maybe some of you can answer that just intuitively. I mean, if we imagine that we have wealth equality, then the poorest 1% of the country would control what percentage of its wealth?
1%.
1%. So wealth equality looks like this. And because the Lorentz function is defined in terms of proportions, it exists on the square. X goes between 0 and 1. The Lorentz function goes between 0 and 1. And here is wealth equality. Well, there is no country on earth that has this as its Lorentz function. A real Lorentz curve might look something like that. Notice that the real Lorentz curve a few properties it has to have. It has to be less than x. If the Lorenz curve were greater than x, that would mean that the poorest people in the country control a disproportionate amount of wealth, and that doesn't make any sense. The Lorenz curve has to always be increasing. It doesn't make sense that the richest 50% could control less than the richest 40%, or the poorest, I mean. So, and it has to start at 0. The poorest is 0% control no wealth, and it has to go up to 1. The poorest 100% of the citizens control all the wealth. And we can then ask, well, how much inequality is there in this country? And we say, well, that question, if we look at this Lorenz curve, and we compare it to that second Lorenz curve, let me maybe actually just draw two curves rather than try to do this on one axis. Comes closer than the one on the left. On the right, the Lorenz curve comes close to the equality curve. On the left, the Lorenz curve is far away from the equality curve. And if we're talking about curves being close or far away, well, there's a very that those curves are close together, so the area between them is small. These curves are so the area the curve if it's small, inequality. And so the area between these curves is the x. And then economists take this and they modify it just to every no reason except that they like nice numbers, I guess. This area is stuck between 0 and 1/2. and it's stuck between 0 and 1/2. No, because it's stuck inside that triangle, and that triangle has an area of 1/2. The base is 1, the height is 1, 1/2 the base times the height. And people say, well, it would be nicer if we had a number between 0 and 1. So they just take that number and double it. And this is the Gini index. So just out of curiosity, America is better than some and worse than others, as you would probably expect. Canada has less wealth inequality than us. Their Gini index is sitting at about 0.33. Finland and a lot of countries around there have even less, about 0.274. The USA is sitting at about 0.411. Countries with Mexico is 0.45, and for a country with Africa, at about 0.63. So I go through this example. I mean, it's not in the textbook, but I think that it's important to understand where area is used, because this is something that the textbook doesn't emphasize and that the textbook should emphasize. The textbook is going to give a bunch of geometric material, like it's going to talk about area between curves, and then it's going to talk about like volumes of these solids. And what the textbook doesn't really make clear is that the volumes, well, I probably shouldn't talk down material I'm going to cover, but the volumes are just kind of messing around, whereas the area isn't. The area is how calculus gets used in a lot of applications like this one. So, okay, I'm going to call this here. I don't believe in 75-minute lectures. We'll continue talking about area between curves in class tomorrow. We'll do some more examples and look at some problems. 14 seconds.
I was like thinking about it.
Not take long for technical